We live our lives submerged in an invisible ocean, a sea of air that surrounds us, constantly interacting with everything we see and feel. We rarely stop to consider the subtle forces at play in this ocean, forces that govern the flow of air and water, forces that enable birds to soar and planes to take flight. One such fundamental principle, a cornerstone of fluid dynamics, is Bernoulli's theorem. It reveals a hidden relationship between the speed of a fluid and its pressure, a relationship that explains phenomena both mundane and extraordinary. Picture an airplane, poised on the runway, engines roaring with anticipation. As it accelerates down the runway, something remarkable happens. The wings, carefully crafted with a curved upper surface and a flatter underside, begin to generate an upward force lift. This lift, the force that counteracts gravity and allows the plane to ascend, is a direct consequence of Bernoulli's theorem. Air flowing over the curved upper surface of the wing has to travel a longer distance compared to the air flowing underneath. According to Bernoulli's theorem, this faster-moving air creates a region of lower pressure above the wing. Meanwhile, the slower-moving air below the wing generates a region of relatively higher pressure. This pressure difference, high below and low above, results in a net upward force lift that pushes the wing and therefore the plane upwards. The shape of the wing, known as an airfoil, is meticulously engineered to optimize this pressure difference. The greater the difference in pressure, the greater the lift generated. This is why planes need to achieve a certain speed during takeoff to generate enough lift to overcome their weight. The principles of lift extend beyond airplanes. Birds, with their specially adapted wings, have been harnessing Bernoulli's theorem for millions of years. The next time you see a plane soaring through the sky or a bird gliding effortlessly on air currents, remember the invisible forces at play, the delicate dance of pressure and flow dictated by Bernoulli's theorem. It's a beautiful example of how a seemingly abstract scientific principle underpins some of the most breathtaking phenomena in our world. Bernoulli's theorem isn't confined to the sky. Its principles are hard at work in countless applications here on the ground. Take, for instance, the carburetor, a device found in older cars that was essential for mixing air and fuel in the correct proportions for combustion. The carburetor utilizes a constricted section of pipe known as a venturi to create a region of low pressure, effectively sucking fuel into the airstream. As air flows through the carburetor, it encounters this narrowed venturi section. In accordance with Bernoulli's theorem, the air speeds up as it squeezes through this constriction, causing a drop in pressure. This low-pressure region within the venturi acts as a vacuum, drawing fuel from a reservoir and mixing it with the fast-flowing air. The fuel-air mixture is then delivered to the engine cylinders for combustion. The venturi effect, a direct consequence of Bernoulli's theorem, finds applications in a wide range of devices beyond carburetors. Aspirators, used in laboratories and medical settings, employ the same principle to create suction. By passing a stream of fluid through a constricted tube, aspirators generate a low-pressure zone that can draw in and transport other fluids or gases. From the mundane to the essential, Bernoulli's theorem is woven into the fabric of our technological world. Understanding its principles allows us to design and optimize devices that harness the power of fluid dynamics, making our lives more efficient and enabling a wide range of applications across various fields. Picture a fast-flowing river suddenly encountering a wider, shallower section. The water doesn't simply spread out evenly. Instead, it undergoes a dramatic transformation known as a hydraulic jump. This abrupt change in water level, often accompanied by turbulent, swirling motions, is another fascinating manifestation of Bernoulli's theorem in action. As the fast-flowing water enters the wider section, its velocity decreases. Bernoulli's theorem tells us that this decrease in velocity corresponds to an increase in pressure. This higher pressure downstream pushes back against the incoming flow, causing the water to pile up and create a sudden increase in depth, the hydraulic jump. But the story doesn't end there. The hydraulic jump isn't just a change in water level, it's also an energy conversion process. The high-velocity flow upstream possesses a large amount of kinetic energy, the energy of motion. As the water undergoes the hydraulic jump, some of this kinetic energy is converted into potential energy, the energy associated with position due to the increase in water level. This energy transformation is never perfectly efficient, and some energy is lost to heat and sound due to the turbulent mixing within the hydraulic jump. Engineers and scientists carefully study hydraulic jumps, using Bernoulli's theorem to predict their behavior and design structures that can withstand their forces. From the crashing waves on a beach to the design of spillways and dams, understanding hydraulic jumps is crucial for managing water resources and ensuring the safety of our infrastructure. How do we measure the speed of something invisible, like the wind or the flow of air over an airplane wing? The answer lies in a clever device called a pitot tube, named after its inventor, the French engineer Henri Pitot. This deceptively simple instrument relies on Bernoulli's theorem to provide accurate measurements of fluid flow velocities. Imagine a tube bent into an L shape, with one end facing directly into the oncoming flow. This is the basic design of a pitot tube. As the fluid enters the tube's opening, it comes to a stop at a point called the stagnation point. At this point, the fluid's velocity is zero, and its pressure is at its maximum, known as stagnation pressure. Simultaneously, the pitot tube also measures the static pressure of the fluid, the pressure exerted by the fluid on its surroundings. This static pressure is measured through small holes along the side of the tube, where the flow is undisturbed. The difference between the stagnation pressure and the static pressure is directly proportional to the velocity of the fluid. By measuring this pressure difference, usually with a pressure gauge connected to the pitot tube, we can calculate the fluid's velocity using Bernoulli's equation. Pitot tubes are essential instruments in aviation, used to determine an aircraft's airspeed. They're also used in wind tunnels to measure the flow characteristics of airfoils and other aerodynamic shapes. From measuring wind speeds to ensuring the safety of our aircraft, the pitot tube, a testament to the power of Bernoulli's theorem, allows us to quantify the invisible forces shaping our world. Bernoulli's theorem stands as a testament to the power of human curiosity and ingenuity. From a simple equation describing the relationship between fluid speed and pressure, we've unlocked a deeper understanding of countless natural phenomena and engineered a wide range of technological marvels. As we've seen, Bernoulli's theorem is much more than a scientific curiosity. It's a fundamental principle woven into the fabric of our physical world. The next time you see a plane soaring overhead, a kite dancing in the wind, or even just water flowing from a tap, take a moment to appreciate the invisible forces at play. The subtle dance of pressure and flow dictated by Bernoulli's elegant theorem. It's a reminder that even the most complex phenomena can often be traced back to simple, elegant principles that govern our universe.